In this video, we are going to be looking at operations on functions and at linear functions. We're going to start with section 1.2 on operations on functions. What we mean by operations are adding, subtracting, multiplying, and dividing functions. So if you see f plus g of x, that just means you're going to add the two functions. F minus g of x means you'll subtract them. If f is written next to g of x, you'll multiply and divide. When we talk about the domain being the intersection, this symbol means intersection. What we mean is where the two functions overlap. Let me show you what that looks like. So if we had these two functions, f and g, and f was my purple function here, which existed from negative infinity and stopped at positive 1, and my g function existed from negative 2 here, and then went on to infinity to the right. The only place where they overlap would be here from a negative 2 to 1. That's where the two functions overlap. So the domain, if you were to combine these two functions by addition, subtraction, multiplication, or even division, would involve only the values from a negative 2 to 1. That's what we mean by the intersection, where they overlap. Let's try this in example 1. So for f plus g of x, we would be looking at adding my f of x function, 1 over x minus 2, plus my g of x function, which is the square root of x. At this point, we won't ask you to simplify, and you're done. That's all that required. But it does want us to look at the domains. So as we look at these domains, looking at my f function, f of x domain, I can see that I have a fraction. And when you have a fraction, the denominator can't equal 0. So if this x minus 2 can't equal 0, if I add 2 to both sides, I get x can't equal 2. So the domain of my f of x function would be from negative infinity to 2, but not including 2, and then from 2 to infinity. We would write it like that. If I look at my g of x function, let's do that in maroon. The g of x domain would be, let's see, underneath a square root, you can only have values that are 0 or positive. So here the domain is including 0 and to infinity. Let's look at where these domains overlap. Drawing a picture of these domains, my f of x function has a whole of 2, and my g of x function starts at 0 and goes on to infinity. So the only places where they overlap are from 0 inclusive to 2, and then it hops over 2 and continues in that direction. So my domain here, we'd write, is from 0 to 2, not including 2, and then from 2 to infinity. Now, if we go on to part B here, it wants us to find f minus g of x. So we'll just have essentially the same thing as we had above, except we're subtracting the square root of x. Now, the domain again is the intersection of the two domains. So the domain for this one will be the same. It will be from 0 to 2. And, no, excuse me, that should be a parentheses because it does not include 2. Then from 2 to infinity. Here, f times g is what you would think. It's going to want us to take 1 over x minus 2 times the square root of x. We can put that over 1. We could clean that up to simply be the square root of x over x minus 2. It will have the same domain, which would be the overlap. So from 0 to 2, not inclusive, and then 2 to infinity. Looking at f divided by g, we would simply have the 1 over x minus 2, but that would be divided by the square root of x. All right, so this is going to get a little more complicated. but we can figure it out. I am going to simplify that, but let's look at this domain for a moment. In this case, we know our denominator can't equal 0. So g of x can't equal 0, whereas otherwise, we said that the domain of g of x did include 0. So the only difference in our domain here on this one is going to be the domain starts at 2 but not inclusive. Now, if we simplify this, we know that when you divide by a number, you multiply by its reciprocal. So when we multiply this by its reciprocal, it would be like that. Cleaning that up, you could write it as the square root of x times x minus 2 like that. Oops. So that's how we'd look at those. Let's continue this by looking at part B. If we take f plus g of 4, we could go back up here to our f plus g function and then substitute 4 in for the variable. So we'd have 4 minus 2 in our denominator here, plus the square root of 4. We always want to simplify these if possible. So we'll have 1/2 plus 2, or 2.5 could also be written as 5/2, or 2.5. If we look at f minus g of 2, it'll be very similar. 1/4 minus 2, except here we'll subtract, oops. We want to substitute in 2 in this case. So we're going to go back to this function and substitute in 2, and then minus the square root of 2. You can see we have a problem here, but 2 isn't in our domain. Recall 2 is not in our domain, so this does not exist. We can have the same discovery as we look at f times g of -3. Our domain does not include any negative numbers. So this one does not exist. We'd find we had a problem when we tried to substitute the -3 into the square root. And here, f divided by g, we cannot have 0 in the division. So this one also does not exist. Let's go to our next page. In the next section of notes here, we're going to look at composition of functions. So composition of functions takes, we use this symbol with this little circle here, and it's the composition of f and g. The way it is written is that the second function listed here will be put into the first function. So let's say, for example, that f of x is the square root of x, and g of x is x squared plus 1. So f composited with g of x, f of g of x, would be taking the x and putting it into the g of x function first. So that would turn it into x squared plus 1. Then we'd take this and we put it into the f of x function, and then that would square root it, because that's what the f of x function does. Let's look at it with example 2. Here we want to find f of g of x. So what that means is f will be the outside function and g of x will be the inside function. So my outside function, let's look at the inside function first. We're going to take this x minus 3 and substitute it into the f of x function. So our resulting function will be x minus 3 quantity squared. If we do it in reverse, g of f of x, in this case, we want to put the f of x function into the g of x function. So this f of x function will go in wherever we see the x. So instead of being an x, it will now be an x squared minus 3. Now with compositions of functions, we have to be mindful of the domains also. If we look at both of these functions, well, let's look at the inside of both of the functions. Starting with f of g of x is my inside function, and g of x just has x minus 3. If we look at x minus 3, there is nothing that x cannot be. There are no restrictions on x. It could be negative, it could be a fraction, it could be 0. So its domain is all reals. Now we're substituting that into a squared function, which likewise has a domain of all reals. So the domain for both of these functions could be written as negative infinity to positive infinity, or sometimes we write it like this, where x is an element of R. Now let's go ahead and check out g of 5 and f of g of 5. If we look at f of g of 5 first, that means we're going to this function, we're substituting 5 in for x. So we'll have 5 minus 3 squared. 2 squared is 4. If we go to g of f of x, or 5, we'll be going to our second function and substituting 5 in. So we'll have 5 squared minus 3, or 25 minus 3, which is 22. In example 3, we're going to want to break up this composite function. So it says that this function is the functions f and g composited together. Or we could say it like this. F of x would have an outside function of f and an inside function of g. So looking here, we would check it out, and it looks like the g of x is that inside function, x plus 9, and your outside function would be this part of it, which would be the fourth root. And we just write it as x. Let me show you what I mean. Checking this, we would write capital F of x would be f of g of x, where g of x is the inside function, and that is getting put inside here where the x is in the f of x function. And indeed, that works. In our next video, we're going to be looking at transformations of functions. Thanks for watching.